I'm Alan Mishler. I'm a student in the Department of Statistics and Data Science at Carnegie Mellon, and I'm going to talk about achieving a particular kind of counterfactual equalized odds in risk assessment instruments. So risk assessment instruments are ubiquitous. We've heard about some types of risk assessment instruments today. They ask what's the probability of an adverse outcome for case I. For example, a school district might want to use a risk assessment instrument to assess students' risk of academic failure. Professor Ghani talked about estimating the risk of lead poisoning or adverse police events. These tools are used in all sorts of domains to help decision makers allocate resources and choose interventions designed to mitigate risk. So we've argued elsewhere that RAI's risk assessment instruments usually intend to ask what is the probability of an adverse outcome under a particular decision, often a baseline decision. So we've argued that they're naturally concerned with potential or counterfactual outcomes. So not is student I going to fail because an intervention might change that outcome, that's what it's designed to do, but rather will the student fail if we don't assign them a tutor. So given this, we claim that RAIs require different fairness definitions than what is conventionally talked about in the literature. So as an example, we consider equalized odds. Suppose we have a binary sensitive feature like race, say black versus white students, a binary intervention, whether to assign a tutor, and a binary outcome, academic success or failure. And we're interested in the potential outcome y superscript d equals 0, whether failure will occur if no tutor is assigned. And suppose we have a binary risk predictor r that labels students as being low or high risk of failure. So equalized odds calls for the predictor to be conditionally independent of the sensitive feature given the outcome, and we propose instead using counterfactual equalized odds, which replaces the strictly observable outcome y with the potential outcome y d equals 0. In a binary setting, this is equivalent to saying that the false positive and false negative rates should be equal across the two groups, black and white students. So the goal of our work is to learn an optimal fair RAI, meaning a loss minimal predictor in which the differences in false positive rates and false negative rates across the two groups are bounded by some tolerances epsilon t and epsilon n for the false positive and false negative rates. So we define a loss optimal predictor, fair predictor R star, and now we want to construct best approximation R tilde that we can. So a very popular paper by Hart et al. In 2016 showed how you can post-process an existing predictor to make it satisfy conventional equalized odds by introducing randomness to equalize the error rates. And here we show how you can do the same thing with counterfactual equalized odds. So here we consider post-processing a binary predictor. So given some input predictor y hat, we flip it with some probability theta little a y hat that's conditional on y hat and the sensitive feature. This generates this new predictor r theta. And what we want to do now is learn these flipping probabilities in such a way as to minimize loss while satisfying this fairness definition. So it turns out that the parameters of our new classifier R tilde can be expressed as the solution to a linear program, which is efficient and easy to solve. And the coefficients alpha hat here that define the linear program yield doubly robust estimators of the risk and the fairness constraints. That's a term from causal inference. And this double robustness leads to nice statistical properties for R tilde. So in particular, we show that R tilde converges to this optimal fair predictor R star that we defined earlier at fast rates and rates under certain relatively mild assumptions about how we estimate these coefficients alpha of the linear program that defines R tilde. This requires no parametric assumptions about the data generating process, and it allows for the use of flexible machine learning methods, sort of arbitrary non-parametric methods to estimate those components alpha. The mean squared error of R tilde converges to the minimal possible mean squared error at root n rates. And any excess unfairness, meaning anything beyond this tolerance epsilon that we've specified as part of the estimand, also converges to 0 at root n rates. So once you've estimated this new predictor, or constructed this new classifier R tilde, you naturally want to estimate properties of that classifier, perhaps before you deploy it in actual use. And we show that you can do that efficiently as well at root n rates. So estimate the risk and estimate the unfairness at root n rates. We have ongoing work that extends this to post-processing a score. So not just a binary classifier, but a classifier that gives you a probability of an adverse outcome, and work to build fair predictors from scratch. So there are advantages to post-processing, arguably. There are advantages to building things from scratch, and we want to be able to do both. And we also want to extend this work to other fairness metrics besides equalized odds. So thank you very much, and I'd be happy to take any questions.